One is connecting the manifold, and the other one is connecting the two sheets. In fact, that's another thing. I did the exercise in words, but I have a metric, I have a distance. So I can also say what is the distance between these two sheets. And the distance between these two sheets, you can calculate easily, is the largest eigenvalue, is the inverse of the largest eigenvalue of m dagger m. Okay, so the two sheets are at a certain distance, and this is due by the off-diagonal part of the connection, as you can imagine. Now, when you make a gauge, the distance is like the X field. The X field is what is connecting the two fields. Now, this is the left part and this is the right part, and the X field is the one which appears in the Lagrangian as connecting the left part with the right part. The usual thing, but we will see actually these things. Okay. Now, I have two parts of the action. One part I call the bosonic part of the action because it contains also bosons. The other one I will call the Thermionic spectra, the Thermionic action, because it involves fermions and bosons. There is no part of the action which has only fermions, but one has only bosons. And now, as I say, everything has to be spectral. Now, if I have an operator, I can do two things with an operator, with the spectrum of an operator. A trace and a determinant. I cannot do well, I can do other things, but the first two things that I can do. Both of them, for an unbounded operator like this will be infinite. It's unbounded, so cannot be trace class. But in quantum field theory, we are used to the presence of infinities. Everything is infinite in quantum field theory. So I have to regularize. This is not yet renormalized, it's regularizing. So I have an infinity, I have to put a cutoff, I have to put a limit to it. And so I write this. I take the trace, not of the operator, but I take the operator divided by a lambda. Now, physics is mathematics with a scale. The Dirac operator as the dimension of an energy, and I can do only some, take traces of dimensionless numbers. So first of all, I divide the Dirac operator by a lambda, which is a scale, and I will later on show you what this scale should be. How many giga-electron-volts it should be. And then I take a function, which is a cutoff functions. So, usually, to make life simpler as a cutoff function, one takes the characteristic functions of the interval. So, I basically count the eigenvalues all the way to lambda. So, this is chi, well, 1. So, chi is just the characteristic function of the interval 0, 1. And this simplifies the calculations very much. Otherwise, to have good calculations, is I can take a decreasing exponential. Okay, I have to take. I could take any function which monotonously decreasing, which goes from 1 and goes to infinity. And I should make sure at the end of the day that the physical results do not depend on this cutoff function, because this cutoff is a regularization. I have something which is infinity, and I have to make it to become a finite quantity. Then I will do field theory with this finite quantity, but the final result should not depend on the details. In fact, the cutoff is a good one, but actually shouldn't work, because if I want to prove the Hit kernel expansion rigorously, I should have analytic functions. So I could imagine a smooth function, analytic smooth function, which approximates the result doesn't depend on the kind of cutoff, and also the calculation if the function is.
But the cutoff regulation is not a Bayesian.
is not gauge invariant, but you will see the kernel how things come out. And okay, now I will be more detailed on the renormalization later on, but I will say some more. Let me say, okay, in this case, if I take the characteristic function, this is just the number of eigenvalues smaller than 1. Then what should I do with this action? I put this action in a path integral, which means that I sum over all possible configurations of the field with a measure. And this gives me the partition function of the theory. Then if I want to calculate average quantities of operators, I just put the operator there and I calculate it. So this is what I need. And this is what and read the action, the effective action. And later on I will expand with the heat kernel. Then the fermionic action. The fermionic action in field theory is this. So this is the fermionic Lagrangian. So I have fermion fields, and let me simplify life. So this psi is a column vector which will be all the possible, I put in a single column vector all of the fields. So there will be the electron, the muon, the quarks, and everything. So this is my psi, electron, muon, and everything. Then I should have a Dirac operator, which is something which takes everything into account. And this is the action. This is usually the action. If I have a single particle, this psi will be a 4, will be basically electron, will be the electron, the right and left part of the electron, and the positron, left and right part of the thing. And if I write that, basically this becomes the which is the Dirac action. If I do the calculations of the variational principle, I find the Dirac equation out of this. It's written in the Euclidean signature. Otherwise, here there will be upside bar, and it will be. But then in the Euclidean things, and in fact, this psi bar psi is the proper invariant for spin 4 transformations, which are not the covering of the Lorentz group. So I mean the Euclidean thing. Now the bosonic part is finite by construction, no? Because I have this is a number, and the fermionic part instead all needs to be regularized. And I will present a way to obtain actually the bosonic part from the fermionic one based on the elimination of anomaly which occurred during the regularization. And this is some work which I did with. Oh, yes.
The bosonic part of the action defined through the Dirac operator, and because it's a number, so it's a trace. So why you take the Dirac operator? Not in the square of the Dirac operator?
Is the same.
The same reason.
Yes, because if the function is this one, this is the number of eigenvalues smaller than the cutoff.
But the square of the Dirac operator is, according to Lisnarow's theorem, the curvature automatically comes.
Yes, it will be. I will use Lisnarov. If this is the cutoff, then the trace of chi of d divided by a, by lambda, equals the trace of chi of d squared divided by lambda squared. Because it's the number of eigenvalues, of positive eigenvalues, smaller than lambda, smaller than 1. So d over lambda, so it's the number of eigenvalues of d divided smaller than lambda. Okay? If I square both parts, the number of eigenvalues don't change. No? If lambda is 10, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's all, smaller than 10. And this is the number is the same of this is the smaller than 100, so I get to 81, but the number is always the same. Otherwise, I'll have to make, otherwise here there will be a slightly different function. So it doesn't change. I like to take a slightly changed cutoff function, which is, yes.
But when you take the square, the negative eigenvalues will also become positive and go inside
Yeah,
0, right?
no, because I take the characteristics function between 0 and 1. So if there are negative eigenvalues of d, I don't count them.
What he's suggesting, if you take the square,
Yeah.
you will also get the negative eigenvalues inside that range.
Yeah.
So you will get more eigenvalues.
Okay, yes, okay. No, yes, you're right. There is a 1/2 here.
1/2.
Yes, there is a 1/2. Because I have no boundary. It's always true that there is another function which does the trick. Okay? In case is with the same function, it's a 1/2. There is a 1/2 because I count also the negative one. So here I will have 1, I'll have twice them, and so they have to take a 1/2. Yes. So there is always, if I take the function and the Laplacian, there is always another function which does the trick. In this case, it's just a factor of 1/2. With an exponential, it's just a exponential with a slightly different coefficient. But it doesn't change. Since in the end, things don't have to depend on the details of the cutoff function, then it shouldn't. It's not.
Can I define the bosonic part of the spectral action? The higher order power of the Dirac operator, I mean the trace of chi double prime, the d n divided by lambda n, n is the integer, 1 upon n.
You want to use here d to the n?
Yeah.
I think you could, but we know what to do with this because of Lichner-Ruiz theorem. The heat kernel is for the Laplacian. We know how to do things for Laplacians. Odd powers are, I don't know how to do odd power. They will, you will get the gamma functions again. And I know that you are fond of odd numbers of gamma functions, but this is the best one because you don't have any it's a scalar.
Yeah, and
So-
another point is the fermionic part of the action. We just see the fermionic field, the trace, I mean psi dagger d psi. The psi is a fermionic field. But here, what is the bosonic field? The cutoff function is the bosonic field.
No, it's a number.
No,
It's a function.
no,
This is a
suppose-
number. Here, it is dA.
No,
dA is something like this.
No,
like this.
suppose the Klein got an, I mean scalar field, that L mu phi is the scalar field. So here what is the scalar field for the bosonic action?
It depends on the Dirac operator. It depends on the Laplacian. Actually, I'll see it in much more detail. You have used all the field content. The bosonic field contents is given by this. It's given. I have a Dirac operator. I have an algebra, and then it's cranking a machine. It's just turning something. So you make commutators with the elements of the algebra, and of
Okay, all our gauge field are put in Dirac operator.
yes.
That is
They are not put.
I mean,
They come out of
come
the
out
Dirac
automatically.
operator. Okay, so that's the good thing. Otherwise, I wouldn't fly all the way from Italy to tell, because not every Young-Mills theory comes out of this scheme. The standard model, yes, and very few other models come out. So this is an advantage because it tells you that perhaps it has something to do with nature because it doesn't work for everything. It works for things which are actually real and exist.
And the other point is that in quantum field theory, the Dirac Lagrangian can be bosonized.
Mhm.
So can I bosonize this fermionic part of the action?
I don't know. But to bosonize it means that I should do everything in terms of bilinears of the fermions.
Yes.
Probably yes, but I don't know.
And yes,
I don't know if it's useful, but it could be.
and it seems this is a Euclidean or a Euclidean case. So psi and psi dagger.
Yeah.
Can I say the psi 1 dagger dA psi 2? Yeah.
Psi and dagger are independent, so you can put a 1 and a
And
2
two.
here if you want. Yes.
The same.
And in the last lectures,
Yeah,
to which I will not arrive, in the sense that I have prepared 4 lectures, but I will only do 3 of them, this is discussed in detail because it has to do with the difference between Lorentz and Euclidean. Okay, now let me, probably I will skip this. So this is the fermionic action. And this is formally, now if you write, this is the path integral. So I have to sum over all possible field configurations this action. Okay, so this is the path integral. Now this is an infinite dimensional, horrible mathematically measure. And here I have this action. Now I will not do this in detail because I want to catch up with time another little bit. There is an anomaly here, and because the theory is invariant for this kind of transformation. Okay, so I change the metric, I change the field, and I change the Dirac operator. Here an A is missing. But this is not invariant for this classical symmetry. It's a classical symmetry of the action, but not a symmetry of the quantum partition function. When there is a classical symmetry, which is not a symmetry of the quantum field theory or the quantum mechanics, we say that there is an anomaly. And in order to correct the anomaly, namely to have this to be still invariant, you may change the measure, adding something to the correction of the measure. And see, this kind of thing is like a determinant, but I have to put a scale to the determinant. And if I correct things, I'm skipping it, what you get is that the term that you have to add to the measure to keep the partition function still invariant after this is exactly the bosonic action. So in principle, you could start with the fermionic action, impose Weil symmetry, and find the bosonic action. In fact, when I was giving some seminars in which I was saying instead that in the Bible, the first thing that God says is fiat lux, which means let light be. So he starts with lights. Lights are the bosons. And I was, in fact, instead changing the words of God, say fiat materia. So if you start with the fermions, which are the materia, the matter fields, the materia, then in a background, a curved background, and then you want to preserve the symmetries, then you would get the interacting bosons out of it, out of this thing. But I am skipping it. For what we are concerned is that we have a bosonic action and a fermionic action. And we can start from those without justifications. Okay? But yeah, I'm not allowing questions here because I skipped this thing. So I skipped
the curiosity. It comes from the measure part, which is not
from the measure part, exactly. From the measure part, from the regularization of the measure part, and mu is the normalization point, the point in which you measure the energy at which you are doing experiments. Okay.
So there are two scales, lambda and d.
lambda is the cutoff scale. The mu is the scale at which you do the experiments.
Energy scale.
Huh?
Energy scale.
The energy scale, exactly. Okay, now let me say a few words on the standard model of particle interaction. And this is more geared towards mathematicians, although I will be, of course, very sketchy. And, okay. Now, presently, we have something which we call the standard model, which is a very successful, and several people now starting saying, but probably it's too successful, because it finished, the formulation is quite old, and it's a few decades old, and all the experiments have confirmed it, which is very good, especially if you are Weinberg, Salam, Higgs, Glashow. But if you are somebody who is not those people, something that doesn't work will give you could give you the possibility of doing something important. And what I want to do is to take a simple form of non-commutative geometry and describe the standard model of these particles, which is the one which is investigated at CERN. Usually we investigate the interaction of particles, so not the Lagrangian, by having particles interact. And one of the ways to do that is to smash one against the other. The other way is to see what they did in the early universe. And that's another way, actually this is probably the one that has, certainly the one which has more future, because we are not going probably to build another accelerator. It's already too big, so the next one. But fortunately for us, the supernova and the early universe were doing this, were smashing things, and the early universe had gas of these particles, so you can deduct things. But for LHC, we still have a little bit to go. People were hoping of finding new particles, and they didn't find any new particle. Spectacularly, they found the Higgs that they were looking for, but ideally would have been the ideal, which would have put everybody happy, is to find the Higgs and find something else. For experimentalists, at least they found what they were looking and they didn't find something else. For theorists, it would have been even better if they didn't find the Higgs mechanism. Of course, I wouldn't give this seminar, but we would be in a very nicer situation, because we have to find something completely new. And but unfortunately, that's the situation. The model works very well. The non-commutative geometry which I can describe it is particularly simple, and it's the product of an infinite dimensional commutative algebra times a non-commutative finite dimensional one. And so the algebra is Morita equivalent to the non-commutative case. And so I do have a normal space-time. Okay, again, I excuse myself for being compact and Euclidean. So what algebra should I start with? So I start with the space-time M, and I take functions of M tensored at finite dimensional algebra. Now, what is this finite dimensional algebra? It's almost the first three sister algebra that you can think of. Okay, among the simplest one. One is complex numbers. One is 3 by 3 matrices. And instead of 2 by 2 matrices, I take almost 2 by 2 matrices. I take quaternions. And I will always represent my quaternions as 2 by 2 matrices of this kind. So a quaternion will be a matrix of this kind. X, X bar, Y minus Y bar, with X and Y are complex numbers. Okay, so these are quaternions for me. Now, the unitary elements of the algebra give me what is the gauge group. The unitary transformation gives me the principal bundle, the group bundle fiber, the group fiber bundle which I can imagine, and the unitaries will be U1, SU2. Good thing of quaternions is that, and U3. But then I impose that determinant should be equal to 1, and the unimodular is called. So the unitaries of determinant 1 form the group SU3 plus SU2 plus U1, or times the Cartesian.
So how do you, I mean, why can you demand this extra condition? Like, I mean,
Yes, I tell you, I will be honest. Why do I demand that the determinant is 1? Because I know that I should get SU3 and not U2.
Yeah, I know. But like, I mean, so what's the mechanism by which you can?
I have to give you, in order to do the determinant 1, you are right. I need a representation. So I will represent these objects on the hyperspace with a reducible representation, and I will require that the unitary matrices, which I will, so I have a matrix which is the representation, and I have the unitary parts of it, which are always U3, SU2, and U1, but then in this representation, I impose the determinant should be 1. And this eats up one of the U1s, and I end up with this. Okay, I will say this over and over again because unfortunately it's something that cannot be said in a seminar. But most of the exercise here are really finite matrices, multiplication of finite matrices. And there are miraculous things with that which happen. So you manage to get all of the hypercharges, I will comment that, but you manage to get the standard model. And if one of the parameters of the groups of the standard model had been different, I wouldn't be able to do it. So the standard model somehow emerges of something which works. Other things don't. So it's but unfortunately it's, there are, at least I cannot see some profound reasons, but there must be. But you just take these matrices and you see that with these parameters there are commutations, all the axioms are satisfied. Then you fiddle a little bit and then it doesn't work anymore. Okay, and then
so could you have a difference in mathematically?
Yeah.
Could you have AF to be some of different direct sum of some other matrices?
Very few.
Very few.
Very few.
It's already some restriction from.
Patisalam works. Very few other things will work. And if you impose that should be a manifold, then basically you get Patisalam and the standard model. Nothing else. There is one thing is depends on the Hilbert space that you take. So I take the Hilbert space as a datum, as a starting point of the particle which exists. Now, of course, if you take a different zoo of particles, you will have a different theory. But not every Yang-Mills theory can be in this framework. By far, not every one. If you then, you know what particles are there. You say, I want these particles. And what is the interaction of this particle? You get some strong restrictions. As I said, the algebra must be represented as operators on an Hilbert space, a continuous infinite. So there is a continuous infinite dimensional part, which are the spinors of this time. So my Hilbert space is two parts. Now it's slightly changed notation. It's spinors. This is R4. I'm sorry. And curious thing is that I wrote these things 3 times. Every time I give the talk, I notice the mistakes, and somehow I forget them when I re-prepare the lectures, changing it, not from scratch, but changing something. I always forget that there are these things and I don't see them. So this is spinors on R4 times a finite dimensional space, which is just putting together all of the particles that I know. Particles, antiparticles, and I will now describe what they are.
The leptons and
I will say it's the next slide. I think in a couple of slides it will come. I will say all those figures. Now I need chirality, and usually, as usual, for the continuous part I take gamma 5, and then for the internal part there will be a matrix, which is 1 and minus 1 eigenvalues with left and right particles. And, it will be so very simple. I know which particles are left-handed and right-handed. Now those things are is what I would say the miracles. Now I want to represent this algebra as operators on this Hilbert space, which has a continuously three-dimensional part times a finite part. So my Hilbert space is P naught times S. The grading is given by this gamma, and there is a left and a right part. The J operator has to exchange the two chiralities and conjugate. So the antiparticle exchanges particle with the antiparticle, but the antiparticle of a left-handed particle will be right-handed, so it has to exchange chirality as well. And it's anti-unitary, so it has to make a complex conjugation, basically. I think it's the only anti-unitary operator that we know pretty much. There are others, but then you end up to this. So, what do I take as Hilbert space? I take the usual zoo of elementary particles, and they transform under, they are modules, representations of this group, and they are, and this is important, always, physically is known, they are always either in the trivial or the fundamental representation of the group. Now, this is true for the standard model, is true for Petit-Salam, is not true for SU5 and SO10. But for us, since the elements are the unitary elements of an algebra, they are always in the fundamental representation. I have very few representations of algebras. In a group, I have a lot of representations. But algebras, matrix algebras, I only have one representation. Two, the trivial one and so if I take the algebra of 3 by 3 matrices, there is only one representation. The unitary elements of this is U3, but it's U3 in one particular representation, which is the fundamental representation. I cannot represent the unitary elements of 3 by 3 matrices on something which is not a Hilbert space with 3 elements. Fortunately, the standard model is such that quarks transform as triplets under SU3, huh? And left particles transform as doublets of SU2. And for U1, I have a bit more freedom, which I will now exploit. And there are and when they are not triplets or singlets, are just fundamentals. So right-handed particles are transformed under the trivial representation of SU2, and leptons, which is electrons, muons, etc., transform under the trivial representation of SU3. So the standard model has chosen to use only things, and for under U1 there is you have more freedom, of course, because representation of U1, yeah, there are a lot of them, because any e to the I y theta is a representation of U1. So you can go around many times. And this is the particles. Now, for the benefit of, I have quarks. I have the up quark and the down quark. Their right-handed version are a triplet of SU3. They are, as I said, a singlet of SU2. And then they have this particular hypercharge. So under the U1, which is the father of electromagnetism, they have this hypercharge. Then they make, as left-handed particle, they make a doublet, which is still transforms as a, under strong, SU2 is a strong interaction as a triplet, SU2 is the weak interaction, and this is a doublet, so it transforms as a qubit, now people would say, of SU2. Then there are the right-handed leptons. Leptons don't interact strongly. They don't interact with color. This is color. And the right-handed particles don't interact. They are singlet under the weak interaction, but they have this hypercharge. Now, instead, the left-handed one are leptons, so they don't have strong fields. And then they are a doublet, and they have this hypercharge. And then there are the right-handed neutrinos, which is known, it's not so many years that we know that they are, and they have zero coupling with everything. In fact, they are very difficult to see, and that's why we didn't know that they were there for many years. We know that they are there because neutrinos have masses, and a massive particle must have a right-handed counterpart, but we cannot detect them directly. Now, antiparticles have hypercharge reversed and left exchanged with right. So if I have to consider a right-handed up quark, it will be in a doublet with the down quark. So left changes with right, and but things act on the other side. So what do I have? I have two kind of quarks. Each is scanning in 3 colors, and I have 2 leptons. So this makes 8 particles, times 2 because I have left and right particles, times 2 because they have their antiparticles. And this is 32 degrees of freedom. Okay? Then, and this is a big issue because no one knows why, everything is repeated identically for 3 generations of particles, with only differences the masses are increasing. It's not proven for neutrinos, but probably slightly. So the masses, and this prompted Isidore Reilly to ask who ordered this. There is no reason. The world would be very different, but somehow everything is repeated three times. I don't know if you are a fan of Arthur C. Clarke and Rama, the book on science fiction. Ramans do everything in 3. It's a science fiction book. There are no fans of science fiction here. It's, okay, science fictions would resonate there. Something appears in the sky, and the Ramans, everything is in triplets. And so the quote is sometimes done is that Arthur C. Clarke's Ramans do everything in 3. The grand total is that I have 96 degrees of freedom internally. Okay? So my Dirac operator, the finite part, will be a 96 by 96 matrix. That's.
So even leptons will have 3 generations?
Sure. Muon, electron, muon, and tau. Electron, muon, and tau are the 3 generations of the lepton. Then up, strange, and top. Up, charm, and top, and top. Down, strange, and bottom. They are the 6 quarks in increasing masses. And one interesting thing, the hierarchy of masses is also very strange, and we are not going to explain. But the top quark is way more heavy than everyone else. So it's about 150 gigaelectron volts. The second one is 5 electron volts, which is the bottom. So there is a big, and then from then more or less they go. You can find something decreasing in a. Then you have another even bigger gap from the electron to the 3 neutrinos. 3 neutrinos are really masses which are, well, I say it at some point, they have masses which are millions of times smaller than the electron. So there is a. Now this will be important in the ghost fourth lecture. There is an overcounting because I have a quadruplexion of states. Why is that? Because you see, I have to take the product, or where it is, of spinors times this internal space. Now in this internal space I counted electrons left and right and positrons, the anti-electrons. So I counted this 4. But then when I counted here this 96, I counted here electron, left and right, and I say that there are antiparticles. So I have an overcounting things. This overcounting is called for historical reasons fermion doubling, because there is a part which is harmless, which is really an overcounting, but another which is more dangerous, because I have an overcounting of left and right-handed particles. So they are particles of an uncertain chirality. They are slightly more dangerous. So the original paper was called fermion doubling, but this really is a quadruplication. This quadruplication has to be taken away with some projections. In the 4th lectures, I would show, if I get there, that this projection is actually very much related to the going from the Euclidean to the Lorentzian signature with a weak rotation. So it's actually good that there is this overcounting, because when I have to identify psi dagger with psi, they go away with this. So the two things are connected. Okay? And okay, now I have to represent this algebra AF, which, as I said, is 3x3 matrices, quaternions, and on this HF. And there are some constraints. The quaternions must represent SU2, so they must act on the particles which are non-trivial under SU2, which are those. Okay? So quaternions have to act on this non-trivially, and as the identity or a 0 on these other ones. Same thing is true. 3x3 matrices have to act on those, but not on those. So I have this 96 thing repeated in some way. I have to have a representation, and I have to take this 96 by 96, and then I have to satisfy other things, because here there is a missing bracket. The commutator of the algebra with j dj must be 0. And then I have to have the chirality must have the right things. And so I will not give the expression of the representation. I can write it. Really, the easiest thing is to write it as a 96 by 96 matrix. But then it takes the whole thing, and you just see lots of zeros, because of course it's a reducible representation of diagonal. Or you can say on each thing indices how it acts. So in the papers, of course, they are there, but in flashing this big matrix is not really necessary. Incidentally, when you're really doing calculations, you write the 96 by 96 matrices on Mathematica, and you verify. Actually, later on for our work, we went to 100. We had bigger things to solve the problem of the mass of the Higgs, so they were 512. So you can still do things by hand, but by far the best thing to do is to put it on a computer with mathematics and have your idea and make the multiplication of matrices. Then you understand the picture, and when you write the paper, you don't do it. You write in the representation of the group on the parts, etc. But it's really, I will not write it, but if you really work on it, there are not that many people that have actually done it. I actually have it in the next file. If you want, I can show it to you. But if you really work on it, you see that it's quite a miracle. So you manage to find this representation with all the constraints, and somehow you start with, can be anything, but then you say, okay, this block must be 0, you don't want to get to this one. And you see that things work. And it's, you clearly see that with a different choice of groups and things, it wouldn't work. So with this, so it's a particle. And one important thing is that the representation does not act in the same way between particle and antiparticles, but the symmetry is restored if you act on the other one with the opposite algebra. So you act on particles on the left and on the antiparticles on the right. Okay, but the two actions commute. And how do you implement this left and right by hitting this J, which exchanges particle with antiparticles. So let me see. Okay, this is. And I still have to give you D. This D will carry the metric information of the continuous part as well as the internal part. D is the one, no, it's not the cancel, it's the one that I was discussing before. So there is a continuous part, but now I put a background. I put an omega mu, which is the Levi-Civita connection. So I am in a curved background. I'm not doing quantum gravity. So gravity is a background, but is not a degree of freedom. I will let oscillate and fluctuates the gauge symmetry. So the fiber band or part I will let, the manifold is fixed, is not changing. Why is that? Because I don't know how to do quantum gravity. If I put the fluctuations of the space-time into the game, then I get a field theory which is non-renormalizable, and I don't know how to use it, and that's why I don't know how to do quantum gravity. So otherwise, if I knew how to do quantum gravity, I would have started from quantum gravity, and this room would be packed, jam for the Nobel laureates, Fedele, Lizzi, describing quantum gravity. I would probably be big.
But I thought that your spectral action gives the root GR, the Einstein-Hilbert action also.
Yes, but
so the dynamic it automatically gives the dynamic.
It's there, yes. But then I don't quantize that when I do the calculations.
Just being a classical action.
Classical.
It's a classical action. When I quantize, I don't quantize it, because otherwise it's not normalized.
No,
So,
okay, you don't quantize it, but the fact that you get a classical.
I do get the classical action. Yes, I do get.
So it should not be termed as a background. I say background
No.
means you do not evolve it.
Okay, but I don't quantize it.
Yeah.
Okay. Yes.
So you can.
When I do the quantization, then I will be on flat space-time, calculate the masses, etc. No, this was for mathematicians. For us, it's obvious. If I write something with for a physicist, if I write something with the Einstein-Hilbert action, I know that I'm not going to quantize it, because otherwise it's not normalized.
Sir,
Yes.
so these Dirac operator is Hermitian,
Yes.
but gamma mu del mu is not Hermitian. I del mu.
There is an I missing. Yeah, there is an I missing. Okay, sorry. This is anti-Hermitian, and ID is the one which is Hermitian.
ID.
Yes, okay, and occasionally, this depends on the convention, depends on which paper I take. If you use gamma mu, the mu is not Hermitian. Okay, so it's it's ID mu gamma mu.
No, the spectrum of the Dirac operator is a real.
Yeah, ID.
With an I.
With an I.
With an I.
With an I.
Okay.
Otherwise, it's pure imaginary.
Imaginary.
Yes. So in general, there should be an I here, really, for everything. So this is a symmetric
Or I don't know, it's a Euclidean case, gamma matrix. It's anti-Hermitian, no?
Yes, you're right. For admission, there
For
is no
Euclidean
I.
case,
Yeah, so they are anti-Hermitian.
anti-Hermitian, and gamma is anti-Hermitian. The both
Yeah,
are
so,
Hermitian.
yes.
Not required I.
There must be an I here on the
Yeah,
Levi
I is
operator.
here.
Yeah.
Right.
Yes. And where the presence of gamma phi, okay, the same for technical reasons as I said. And so this DF is a 96 by 96 mark. Let me see if I can get. I will, if there is a question. Okay, I will just say the fermionic action and then I will stop, because the bosonic one will take a little bit longer. And I have this J. See, I act on particle and antiparticles in an asymmetric way, but they need J. So the fluctuations of the Dirac operator I should take into account the fact that I want to act on particles and antiparticles. So I will not only take the connection one form A, but I will only take the opposite one. Or if you want, I will have the connection act on the Hilbert space from the left and from the right. Okay, so this is the Dirac operator, the covariant Dirac operator. And now I will not again give details, but you have to take the commuting is cranking a machine. So you have these huge matrices, you have this slash, and you have to commute with these elements of the algebra. And this commuting 96 by 96 matrices written in whichever way you want. You can, and then the commuting part of df with the elements of the 3 by 3 will give gluons. Commuting with the quaternions gives W, and commuting with U1 gives the B field. Those are the bosonic particles that people look at the LHC. In particular, the gluons are confined inside of the quark, so they are not seen directly. The W's were seen in around 80. The Z a little later, and the combination of this with B has been seen always because it's the photon, it's light, so it's the one we see by which we see each other. But then there are also the fluctuations in the internal space, and I should write the fermionic action. And for internal reason, there is this J which is happened here. But now I have to give you this df in detail. So what I will use for the internal part of the operator, I will use all of the information which I have about the masses of the fermions. Okay? Because this M is the one, as I showed you when the 2 by 2, is the one which connects the left with the right part, and gives in the simplest case the mass part of the Dirac equation. And so I will put there in these 96 by 96 matrices in the appropriate places, which when the right electron connects with the left electron, I will put there the mass of the electron. There are some mixing between the states, which is called Kobayashi-Maskawa mixing, and I will put there. So this 96 by 96 matrix is mostly empty, but there are a few numbers, which I know from experiment. Okay?
So why insert the J?
Huh? Because I am in the Euclidean case, but I want to put, if I don't put this J, this is psi dagger, and then there is M here, I would have that the terms of mass, I would have left electron with left electron.
Yeah.
Okay? And I don't want that. I want right electron with the left electron. But J exchanges particle with antiparticle in the two chiralities. So I get the proper way. The mass term connects the antiparticle with the other opposite chirality to the particle. So for the electron, the term that I have in the Lagrangian is E bar L M ER. No? Without the J here, I would have EL M ER.
M is the equal matrix.
No, M is the mass of the electron. Okay? So if I write without this J, okay, here I have E right, M E right. Okay? Or probably, or this. I get this. Okay? And then I want this. With J, which exchanges particle with antiparticles, I get this.
So
this is the term.
gamma
Huh?
zero. Gamma zero.
J plays exactly the role of gamma
Gamma
zero.
zero.
Okay? To do the
Not
Gamma
very
zero.
good.
huh?
You are in Euclidean space.
Yes, but both of them.
But then he needs to have terms like this.
J,
bar,
J,
bar.
J, everything here is a matrix, okay?
No, no.
And J
But then
is
why
the
he
following
needs
matrix.
Right, the Euclidean space.
Everything is, I have a 96 dimensional, so J is this matrix. 0, 1, 1, 0, and then complex conjugation. This is the anti-unitary operator.
No, sir. Why we require this term? Because we are in the Euclidean space. So there, the first term is the phi L bar psi r is the Lorentz invariant. Psi L bar psi r.
Yes.
Euclidean means you have to invoke SO4 invariance.
No, if you just start a first principle, so you write psi L bar psi r is the Lorentz invariant. But here we not require any Lorentz invariant. It's SO4 invariant. So in SO4 invariant case, we not.
Can we not have terms like ER bar, ER? What is
I want this because I know the answer. Okay, so I want to, the game is that I reproduce the standard model action, but I save on one parameter. So I want to reproduce the action. Okay, if I do, and with this J, I reproduce the action. In particular, with this J, if I do the transition, the partition function, this becomes a Farfian integral. Take into account, I'm not saying it, that this psi in the game, they are operators. They will become operators. They are anti-commuting fermionic operators.
So anti-Euclidean.
Yeah, it's the
Anti-Euclidean, right?
yes. In the end, I will have to do this. And
So
this is the,
you are formulating initially in terms of Euclidean variables, but now you want answers like in a Minkowski.
I
type.
want to reproduce the one,
Minkowski type answer.
yes.
The final
Because
answer.
then with the anti-rotating, I should find a good one. So I put a J in here. It's actually not completely also necessary. I could make things more complicated by taking df much more complicated than that. But this way it works. And in this df, I put all of the masses and mixing, which I know. So all of the parameters of the fermions. And this is the calculation. To calculate this d8 is completely straightforward. It's really commuting 3 by 3. It's a 96 by 96 matrix, but it's in blocks of 3 by 3 and 2 by 2. So it's really commuting matrices of at most rank 3. Let me see. No, this is now. This I will need more time because it's the heat kernel expansion. So I will do it in more detail. The bosonic action. So the fermionic action I just reproduced.
So they also need some half factor, no?
Yes. And with this alpha, but if I do it tonight, but then I'll have to change it on here. If I do it on time, I'll change the factor. I have to, okay, I will finish on this half factor. Okay, I don't know how many 2 pi's were lost in this. So I use this approximation in which 2 pi equals to 1 equals to I. This is my, that's the units of measurement which I use. And of course, you can prove that then is equal to 1 alpha as well, without any problem. It's like, from this you can prove everything else. Okay, I will stop here for today. Oh, actually, I must stop here.